Université Paris-Dauphine, and we'll speak about Liouville quantum gravity on the Riemann sphere.
I have changed. I am now in Marne-la-Vallée. It's not visual. Okay.
Oh, sorry.
I will tell them. Okay, so thank you. So before I begin, I want to say that I am a bit in trouble with my English. So I apologize for this, but well, you know, when there is no harm, there is no pleasure. Okay, so so maybe So I want to discuss quantum field theory, which is called the Liouville quantum field theory. And maybe as an introduction, yesterday we had a very nice talk by Clément Angler, and I can try to make a few connections, and there will be a few connections, and also some differences between my talk and his talk. So let us say that Clément yesterday introduced the Ising model. Well, he didn't introduce the Ising model, but his presentation was about presenting this model as a conformal field theory. So this will be CFT in my talk. And he said that there are two important fields in this conformal field theory. So which is called primary. So there are, say, two fields. Well, important, say. So there are the spin and the energy. And he explained that he carried out his approach from for the construction of his Ising model from discrete to continuum. Well, what I want to discuss today is a construction of another conformal field theory. So, and this will be the Liouville conformal field theory, because it is both a quantum and conformal field theory. So the difference is here that I will get actually a whole family of conformal field theory, which are indexed by a parameter gamma. So this will be a CFT indexed by say a parameter gamma, and for each gamma you have a different conformal field theory. So the difference is now in this, for each value of gamma, inside a fixed CFT with parameter gamma, you will have an infinite number of primary fields, of important fields if you want. And more or less these fields will be described as the exponential, say, of some phi, some field phi, which is called the Liouville field. And this law of the law of this field will be given by some probability measure on the space of function. And I want to describe how to construct this probability measure. And the difference here is that I will we have a construction which is directly in the continuum. So well, so if you have this picture in mind, what I want to do is in my talk, so I will make a short introduction to the motivation from physics, but then I will explain which is what is not in my picture here is the connection between my construction in the continuum and the related discrete models. So this will be the point 3, and in order to explain this connection, I will have to first recall a few facts of Gaussian multiplicative chaos theory, and then in the end I will more discuss this Liouville QFT. So I will use for Liouville quantum field theory, I will use as a shortcut Liouville QFT. Okay, I will discuss more this Liouville QFT from the angle of conformal field theory. And in the last part, if time permits, I will discuss a lot of properties that you have and which are very similar to the Ising model. And these are some points that Clément discussed yesterday. Okay, so let's begin. Before I start, I would try to explain something very simple, and maybe it will help you to understand how it works, this construction of the Liouville action. So let's take a very simple example on R. Take a functional. I mean a function, a very nice function. Take say x squared over 2. Okay, this is a very nice function. Okay. It has a minimum. Okay. At 0. And if you want to construct a probability distribution out of this function, you just take a parameter beta and construct, say, a probability measure, which has this density here. So you just weight the uniform measure on real numbers by the exponential of your functional. Okay. So for the Liouville quantum theory, this works pretty much the same, except that instead of integrating some exponential of functional against real numbers, you will integrate against a uniform measure on functions. So the framework is more or less the following. I want to write the notation somewhere on the blackboard because I will use them throughout my talk. So you've got a Riemann surface, a two-dimensional Riemann surface, call it M. It is equipped with a metric, call it G. And when you have a metric on a Riemann surface, so this is two-dimensional, you can define a volume form. Okay, for instance, if you are on Euclidean space, this is just the Lebesgue measure. Okay, you can define the Ricci scalar curvature, and as I will discuss the construction on the sphere in most of my talk, the Ricci scalar curvature will be 2. So this is the Ricci scalar curvature. You have also some kind of Laplacian associated with this metric. This is the Laplace-Beltrami. And I will also have a gradient on this manifold. Okay. So if you fix, say, a manifold, you have a metric on this manifold, and you can define a functional. So this will play that acts on a function on your manifold, and this plays the role of my A here in my very simple example. So this functional here is called the Liouville action, okay? And basically, what you want to do is to construct the partition function here. So this kind of things here. You want to define this partition function, and if you manage to do so, you will also have a probability distribution associated to this partition function. And well, the main purpose of my talk is to explain that we can construct rigorously such a probability distribution. So first, why do we care about this Liouville quantum field theory? Well, first, as I said, this is an example that you can mathematically handle, where you've got a whole family of non-trivial conformal field theory. Second, and this is the point I will discuss further in my talk, this is the connection with the scaling limits of random planar maps. And there are two other important points that I won't discuss today, but there is a lot of ongoing research today between higher dimensional quantum gravity and this two-dimensional, which is apparently a simpler quantum gravity model. Okay, so if you, I will explain during my talk why we focus on 2D. Okay, but the true physical dimension is say 4D, or you have also very interesting model in 3D, and they are all related to this 2D quantum field theory. So this is very important from the point of view of physics. Okay. So so how does this thing appear? So the interest for Liouville quantum gravity is, we'll say that it is born in well in 81 with a paper by Polyakov, which roughly says that if you put whatever it is, a string on a manifold, okay, it will interact with the geometry of your manifold, okay, and in such a way that the geometry will become random, okay, and if you want to describe what is the geometry on your manifold, you will get some kind of well, this will be the reference metric on your manifold. Say if you're on the sphere, this is just the round metric, and you will have a factor here, which is just the exponential of some random function, okay, and this random function is a Liouville field, okay. Well, actually, Polyakov's derivation was very hard to handle mathematically, and when you have something which is very hard to handle in the continuum, usually you want to discretize your model, okay? Because when you discretize something, usually the objects you have to deal with are much more easy to define. And then the problem is to take some kind of scaling limit, okay? This is the random planar maps approach, which has been developed since this paper, and there is a huge physics literature on this topic. Okay, so what I want to do now is to explain this connection. This is just one aspect of this Liouville quantum field theory thing, but I want to explain the connection between the random planar maps and Liouville quantum gravity. So I will first need to recall a few facts about this Gaussian multiplicative chaos theory, and this is what I am doing now. So now I want to explain the construction on the sphere. So the sphere, you can see the sphere as the whole plane, here too, equipped with the round metric. So the round metric is this metric here, and for this metric you can check that, well, if you have an exact definition of the scalar curvature, you can check that this Ricci scalar curvature is 2. Okay, so the first question I want to address is how to define the exponential of some Gaussian field, which is called the Gaussian free field. Okay, and here I want to integrate this exponential against the volume form on the sphere. So recall maybe that the volume form on the sphere is just well, this is just you want to define something like this. Okay, where Gx is just the Lebesgue measure on the plane. Okay, well, this construction is not obvious because you know the Gaussian free field is not a fairly defined function. Okay, this is just a distribution in the sense of Schwartz, and if you want to take the exponential of a distribution, this is not well, it's not completely obvious. So so constructing random measure of this type is well, one purpose of the theory of Gaussian multiplicative chaos. So how does it work? So first, a word about the Gaussian free field. Well, formally, you want to construct a random function. So this random function will be your big X. Okay, and you want it to be centered. Okay, so it's right. You have here. You want it to be centered, and if you have a Gaussian function, so you just need to make explicit its covariance kernel. And you want the covariance kernel to be exactly the green function of the Laplacian on the sphere. Okay. So what it is, you just what is this Laplacian on the sphere? You just try to solve this equation. F is your data, U is the unknown. Okay. And you want to solve this equation with this boundary condition, which is you want your solution to have a zero mean on the sphere. Okay. So this equation has a kernel, a green function, which is given by the g here. Okay. And if you look at the shape of your green function, there is a, well, say, a short-scale dominant term, leading term, which is a log. And then you have behind this singularity here, you have a nice function f. Okay. So, well, this is the formal description you want to have of a Gaussian free field. But of course, this is not rigorous because you see that the variance blows up when x is equal to y. So you have to work a bit and define this. Well, actually, you don't have to work that much, but you can define this random function not as a function but as a distribution. Okay. So what is it? You just act on test function, and you want your distribution to have exactly this covariance curve. Okay. So this is the main properties of the Gaussian free field. So the thing which is very nice with this Gaussian free field, at least on the sphere, is that you can expand the Laplace-Beltrami on the sphere along its eigenfunctions. Okay, and you can even normalize your eigenfunction to have to be an orthonormal basis of L2. Okay, so call En these eigenfunctions, and then you take an IID sequence of Gaussian random variables, which are standard. And here you've got the eigenvalues of the Laplacian. So formally, the GFF can be written as this sum, and this sum converges in some dual Sobolev spaces. Okay, it converges almost surely in some say h minus 1. Well, the dual of the standard Sobolev space. Okay, so you've got a nice representation of your Gaussian free field, and basically this kind of representation is what you need to apply a current theory of Gaussian multiplicative chaos. The thing is that recall that forget for one moment this term here. Okay, you want to define this random measure, and you know that you are dealing with a very bad function. Okay, so the first thing you want to do when you have a very bad function is to regularize a bit your function. Okay, so here, as you have this nice representation, if you want to regularize your field, you want to take the partial sum of your series. Okay, and if you do so, you want to say that the limiting measure you want to construct will be the limit of this approximating measure here without the variance term here. Okay, if you just do this approximation, you will easily see that this random measure without this term here will diverge. You need to renormalize a bit your random measure, and you renormalize them by the mean, so that you so that the mean of your random measure here is just this deterministic measure here. You renormalize by the mean, and if you do so, well, as you have a sum of independent random variables here, you see that you've got a nice martingale here. Okay. So if you've got a nice martingale here, it is obviously positive, so it converges almost surely. Okay, so you've got a limit. The thing is that you don't know if this limiting measure is trivial or not. Okay, and well, Kahn studied these measures, and he showed that if the parameter gamma, which is here, this is a parameter of my measure, if it is small enough, okay, this limiting measure are non-trivial. Okay, and actually, if gamma is higher, the limit that you get is 0. Okay, so you have some kind of phase transition, and so the limiting measure that you get are have some nice properties, like they have a full support. I mean, there is a mass distributed all over the whole plane. Okay, every ball has some mass. And it is diffuse. I mean, it has no atom. Okay, there is no direct masses hidden in your measure. And it showed that the carrier of the measure is the set of well, the so-called gamma sig points. And he also this measure have nice fractal properties. And one way to characterize this is to study the Hausdorff dimension of the smaller set which carries all the mass of your measure. Okay, if you can look at the fractal dimension of this set. Well, and actually, well, this set has Hausdorff dimension 2 minus gamma square over 2. Well, to be fair, can only show that this dimension is greater or equal to this quantity, and he left the other part as an exercise. Okay, and the exercise is not obvious. Okay, it has been proven a bit later by Miller-Pires with a somewhat different notion of gamma sig points than Kahn. And recently, Alessandra Cipriani, who should be here, has shown that all these different notions of gamma sig points coincide, actually. Okay, so, well, this is just a rough picture of the measure you get. And, well, now I'm going to take the whole plane. And the question is, so you take some points in your plane, and the question is, how much can this chaos measure integrate some? Here you have some points zi, and you put some power singularity in your plane, and the question is, how much can this chaos measure integrate these power singularities? Okay. Or you can ask the same question for the Lebesgue measure, okay? And the thing is that this chaos measure, if you fix a point, okay, a deterministic point, this chaos measure have much more regularity than the Lebesgue measure. If you fix deterministically the point, okay? So this is the content of my statement. It says that here you have your chaos measure, and I plug some power singularities, because recall that when x is close to xi, okay, this green function behaves like a log. So you take the exponential. This gives you a power singularity. And so if the alpha I are smaller than q, so what is q? It's not written anywhere, but we can keep this. We can record this value of q. Okay, here. So if you ask the same question without the chaos measure, but just the Lebesgue measure, here you would have the condition alpha I less than 2 over gamma. Okay, so this shows that these chaos measures are locally much more regular than the Lebesgue measure. Okay, so my claim is that this quantity is finite, and it's called the Seiberg bound. And actually, you can check that. Well, between the Lebesgue measure threshold and the chaos measure threshold, you have this measure have infinite expectation. Okay? So there is some kind of different behavior between Lebesgue and chaos. Okay, well, so this is all I need from Gaussian multiplicative chaos theory. Now let's focus on random planar maps. So, well. Now, first, I want to recall a few results about this random triangulation. So, what is roughly a random triangulation? Well, first, what is a triangulation? This is just a gluing of triangles, in order that in the end you get something with the topology of a sphere. Okay, something like this. Actually, you don't care about the shape of the edges. So, these objects, you have a kind of triangulation of the sphere, but if this object, if you look at them up to angle preserving homeomorphism, you will get just a finite number of triangulation with n faces. Okay, so you take a triangulation, you ask it to have n faces, and up to homeomorphism, there is only a finite number of them. So if you have only a finite number of triangulation, you can pick up a triangulation uniformly at random among this finite set of triangulation. Okay. So if you do so, you get a random triangulation of the sphere. Well, the important theorem in the fields are the definition of the Brownian map. So just the thing is that when you have your triangulation, you can consider the graph distance on your triangulation. So the graph distance is standard. Between these 2 points, you are at distance 1, and this one here you are distance 2 and so on. Yes, you put the graph distance on your triangulation. Well, the thing is that now you have a random metric space, and if you take the scaling limit as n goes to infinity, well, this random metric space converges for some topology, the Gromov-Hausdorff topology, towards some random metric space, which is called the Brownian map. Okay, so and this Brownian map has a topology of the sphere. So this was proved by Le Gall and Riemann for triangulation and quadrangulation. But I will also mention another result by Curien and Le Gall, which is the Brownian plane. So if you want to have an intuition of what it is, so let's look at the, well, just try to imagine that you have your Brownian map. Okay. If you like to think of it as a random Riemann surface, you take a point, okay, and you zoom very near this point, okay, and you get something which is called the Brownian plane, and actually you can see it as some kind of tangent plane of your random surface. Okay, so you zoom near a point, you get something which is which looks like a tangent plane for the Brownian map. Okay. So now, well, this is just a record of the existing result. Okay, so I will use them in the following. But well, the thing is that if you want to focus on quantum gravity, you need to reinforce the structure that you have on your triangulation. Okay, so you want to consider a conformal structure on your triangulation. So how to do so? Instead of now, the shape of the triangles that you will glue together will matter, and you will glue equilateral triangles in a combinatorial way described by your triangulation. Okay, so you can do so. This has been done by Gill and Rod, and more recently in a paper by Curien. Okay, so you can equip your triangulation with a conformal structure. Okay, so now you've got a triangulation, a conformal structure. And if you got, which has the topology of a sphere, okay? So you got a conformal structure. This is the point with the topology of the sphere, so that the uniformization theorem tells you that you can embed your triangulation onto the sphere. Okay? So you get something like this. Well, this is just an artistic picture, but. Well, should look like this. Okay. So the question is, what is the scaling limit? What is the scaling limit of this object when you have embedded it onto the sphere? Okay. And now I'm going to, in what follow, I'm going to explain you how it works and what is the scaling limit of this object. Okay. So well, the thing is that I will now consider the set of well, I will now consider the set of triangulation with n marked faces. Okay. Well, when you define your conformal structure on the triangulation, it does not matter if you have marked faces or not. You just glue your triangles as you should do, and you don't care about the marked faces. But well, and if you do so, the problem that you will face is when you will embed your triangulation in the sphere, because you have some degree of freedom. If you take a uniformizing map and to send your triangulation onto the sphere, you can compose with any Möbius transformation of the sphere and get another embedding of your triangulation. Okay. So what I want to explain now is how to fix this degree of freedom. So. Well, the thing is that on triangulation, well, you just consider the partition function here. So here you have a sum over n. Here you have the cardinal of the triangulation with n faces and 3 marked faces. And here you just weight by this exponential term here, and so just in some sense weight by the volume of your triangulation. Okay, n is the number of faces, and it looks like the volume of your triangulation. So this is some kind of Boltzmann weight. And well, there are some theorems which tells you that the number of such triangulation inside this cardinal here, the number of triangulation you get behaves like this, okay? So you have a leading exponential term and a polynomial correction here. The polynomial correction will be very important for me, because if you want to sample a triangulation according to this partition function, you have to make sure that this series here is finite, okay? So if you have this asymptotic behavior here, you see that this partition function is finite, provided that mu bar is bigger than mu c. Okay? So if this series is finite, you can sample a triangulation according to this partition function. Okay? So now, how to fix this Möbius degree of freedom? So you take your three marked faces. So maybe you have your maybe a picture. You have your triangulation of the sphere. Okay, you have marked three faces, or say vertices. It doesn't matter actually. Okay, you marked the three faces and one here, and you want to send this triangulation onto the sphere. Okay, so you will fix arbitrarily 3 points on the sphere. Say x1, x2, and x3. And you will require your uniformizing map to send the three marked faces onto the 3 points that you've marked on the sphere. Okay, so you will send this one here, and this one here. Okay. So once you've imposed the condition that the three marked faces be sent on the three marked points, you get a unique uniformizing map which sends your triangulation with its conformal structures onto the sphere with these three marked points. Okay. So now on your triangulation, you can with this uniformizing map, you will have some weird faces on your sphere, which look like well, very bad triangles. Well, okay. So what you want to do now is to put a mass a square on each face of the thing you get on the sphere. Okay. So in such a way that the volume of your triangulation is now n times a square. Okay, you have n faces with a square mass on each face. Okay, and in this way you can define a volume I mean some kind of volume form associated to your triangulation. Okay, and for which the mass of each face has mass a square. Okay, so so now you've got a random measure on your a random measure on the sphere. If you pick up this random triangulation uniformly at random, okay, you associate the measure that I've constructed here with a mass a square on each face, okay, and you just sample your triangulation according to this partition function here. Okay, you get the law of a random measure on the sphere associated to the triangulation. Okay, so now you want to take a scaling limit of this object. Okay, and if you want to take a scaling limit, you want your partition function to preferably sample these configurations where you have a huge number of faces. Okay, you want the number of faces of your typical triangulation to diverge. Well, obviously, this will occur when the mu bar here is very close to mu critical. Okay, because when you choose mu bar equal to mu critical, you will just get here the sum over n of this polynomial corrections here, and this sum diverge. Okay, so when you are very close to the critical point, your partition function here will diverge. Okay, but we have to make this a bit more precise. So So we assume that you are very close to the critical point up to some constant times the mass that you've put on each face of your triangulation. Okay? So if you are in this regime, the conjecture is that the random measure that you get here associated to your triangulation will converge in law towards something which is called the Liouville measure of Liouville quantum field theory with some insertion points. So these insertion points correspond to the 3 points you've chosen on the sphere. Okay? And they have these insertion points have a mass which is called gamma. And for the context I'm discussing here, the value of gamma is given by square root of 8/3. Okay, and before I give you the exact definition of the Liouville measure of quantum field theory, let me make just a very simple computation that I will need the following. We can try to compute the limiting volume, the law of the volume of your random measure here. Okay, this is a very simple exercise, but this has a lot of consequences. So let's just look at the expectation of mu a bar, what is mu a, sorry, of the sphere. Okay, this is more or less, we can, if you look at the volume, you have on each triangulation n faces and the mass a square on each face, so the volume is just n times a square, times a square. So this is just by definition exponential. But I take a nice functional of my volume. So this is just by definition exponential minus mu bar n f of the volume n a square and times the number of triangulation in this set here. But we have the behavior of this number. This is just exponential mu cn times n to the power, okay? And you divide by the total mass of this partition function. Okay, just get here sum over n, so minus f, no, okay. Okay, so now recall that mu bar, there is a relation between mu bar and mu critical, which is exactly this one. Okay, so you got a sum over n of exponential minus mu a square n. Because I simplify these two terms, you have f of n a square and n to the power. I don't make the simplification here, it's too difficult, okay? So, because I will work with this form in the following. So you just get this, you just got this expression here, and it is very convenient to add a square here and divide by the same quantity down. Okay, so you have this. This is the volume, the law of the volume of your triangulation. And this is just a nice, Riemann sum. You can take the limit as n goes to infinity. And will converge toward some integral. Okay, so you get up to a normalization constant. You will get exponential of minus mu y, f of y to the power written here. So you see that the volume of your triangulation converges in law towards gamma law, okay? And so you get a gamma law. This is a gamma law with parameter 3 minus 5/2 mu, okay? This is a very simple computation. Well, now I'm going to define the Liouville measure that you get out of Liouville quantum gravity, and it is given by this expectation here. So recall that this is the z measure is the measure I introduced when studying Gaussian multiplicative chaos. So you have this power singularities here, and here you've just got the chaos measure on the sphere, okay? And well, the law of the Liouville measure is this chaos measure that you have renormalized by its volume. You weight by some power of the whole mass of the space, and here you have an independent gamma law, which is independent of your free field and therefore from the chaos measure, okay? You have a gamma law here. This is what you get when you have constructed your quantum field theory. It tells you that your Liouville measure looks like this, okay? And here, you have an explicit expression for the gamma law of your Liouville measure. So, if you want your triangulation to be the scaling, if you want this Liouville measure to be the scaling limit of your triangulation, you see that at least the volume of space must be the same as the Liouville of your the volume of your Liouville measure. So you just have to match the exponent here. You have this relation 2q over gamma must be equal to 5 half. Okay, you solve this equation and you find that the square root of that gamma is equal to square root of 8 term. Okay, and recall that we've got this exponent here just on the behavior of the partition function of triangulation. Okay. So you can do this when, well, in a more general context, but when 20 minutes? Well, okay. The thing is that, well, this is the situation. The situation as I described is just called pure gravity, okay? Because there is no coupling of your triangulation with other conformal field theory. You can do so, and you can have exactly the same conjecture. I mean, you look, well, when you couple a conformal field theory with random planar maps, you will not sample your triangulation according to, well, uniformly at random as I did here, but you will sample your triangulation according to the weight, the partition function of your favorite model of statistical physics on your triangulation. Okay? So you will sample according to this weight, and if you look at the growth of your partition function, it will behave typically as I mentioned here in the case of pure gravity, but the exponent will be different. This will give you different values for gamma and for the mu here. For instance, if you put an Ising model on your triangulation, you will get a value of gamma which is the square root of 3. So you have more general situation, and actually all this random geometry that you get in the limit are singular with respect to each other. So depending on the weights that you put on your triangulation, you may get completely different random geometries. Okay, I'm gonna skip. Well, just something I mentioned. Well, the Liouville measure in the literature, depending on the, well, there are some misunderstanding sometimes with respect to this Liouville measure. It is often said that the Liouville measure is the exponential of a Gaussian field, and this Gaussian field is the Gaussian free field. Well, you see here that this is not the case, because this measure, if you want to understand it formally as the exponential of something, because of this weight here, your field will not be Gaussian. And even if you condition on having n faces your triangulation and whatever you do, you will never have a Gaussian field here. Okay, so this is just a point I want to stress. Well, okay, now the question is what is the, well, you may have in mind is what is the relation with Scott construction of quantum cone or quantum, a lot of quantum things. I will focus on the quantum cone. Okay, so, well, this is a picture we have in mind. We've tried to understand what happens here, and, well, I'm gonna explain the picture we have in mind. So, here you've got the sphere, and let us admit for a while that we can construct this quantum field theory. So, you have it's more or less like a sphere, and you have some peaks here which stand for the, well, the points where you have anchored your triangulation. Okay, the marked face of your triangulation have been sent to the 3 points that you've got here. Okay, and because there are typical points for the Liouville measure or for the triangulation as you want, they have some more mass. There is some phenomena which makes them have more mass than the other points of your sphere. Okay, so there are some peaks of mass here, and you may place yourself at the top of a peak and make a zoom very near this point. Okay, make a zoom, and you should get something like that looks like the quantum cone construction of Scott. Okay, so this is a picture we have in mind, and so therefore, well, the intuition that you may have is that if you try to formulate a proper conjecture on the uniformization of the Brownian plane, okay, and I guess Scott knows very well how to formulate this conjecture, you should get the quantum cone in the scaling limit. Okay, so this is just a few. This is just a picture I want to address, but well, this is a work in progress. We have a student trying to make a theorem out of this picture. Okay. So now let me discuss in more details this Liouville quantum field theory. But before I start, I want to try. It's not very easy, but I want to try the picture I have in mind about what is a quantum field theory, because I am probabilist, and this is the way I see the situation. And I don't claim that this is a rigorous definition of quantum field theory, but well, informally, this is a randomization of a classical field theory. So how do you define quantum and classical field theory? You just take Riemann manifold and you define an action, I mean a functional, on this manifold. Okay, it acts on function phi which are defined on your manifold. Okay, and when you've got such a functional, you have two points of view. There is the classical point of view and the quantum. Well, the classical will be to study the minima of this functional. Okay, if you do so, you will get a classical field theory. Okay, so you have a functional, you study the minimum, and you get something classical. And if you want to construct a quantum field theory, you will take your functional, and so you take the uniform measure on function and weight this uniform measure by the exponential of your functional at some given temperature. Okay, well, this is a formal description, but this is more or less how it works. And I think it's nice to have this picture in mind because I can explain a bit how this picture fits to the Liouville thing. Okay, if you want to look at what is this picture in the case of Liouville field theory, the functional that you get is the Liouville action. Okay, this is this action here, and this action is very important in Riemann geometry because well, if you first look at the classical theory related to this functional, you get so you just look at the saddle point of this equation of this functional, you get this equation here. This equation is called the Liouville equation. This is a well known but also an old equation. Okay, roughly it is very deeply connected to the uniformization of surfaces, because if you have a Riemann surface M with a metric G and you want to solve this equation, if you manage to do so, okay, and you define a new metric on your manifold with a conformal, so this is the background metric that you have on your manifold, and just weight by the exponential of your solution. Okay, if you do so, you will get a new metric which has constant Ricci curvature. Okay, and then you say that you have uniformized your surface. Okay, so the classical field theory associated to this action is the Liouville equation, and this is about the theory of uniformization of random surfaces. So the Liouville quantum field theory will be more or less the randomization of this well-known equation. Okay. Well, so just this was for the purpose of this discussion, but this form of the Liouville action is rather unusual. So if you just make a change of variable here, and you just get the standard form of the Liouville equation, and this is with this expression I will work in the following. Okay, so there is a change of variable from going from here to here. It's not quite obvious actually, so that's why I don't give an explanation. Okay, so well, when and if you manage to construct such a quantum field theory, well, the quantities of interest are now let us assume that you have constructed just such a probability law. You get, so you are now having a nice metric tensor, at least formally. If you can describe the law of the Liouville field phi, you are now interested in studying the geometry of some metric tensor on your manifold, which is given by gamma phi. Say we are on the sphere or not? No, not sphere. So if you manage to construct the Liouville field on the manifold M equipped with the metric G, you are now interested in this metric tensor. Okay, this is a metric tensor. The thing is that the Liouville field behaves almost as bad as the GFF can behave. Okay, so that this metric tensor is ill-defined. Okay, it's not clear how to formally you can define a measure, a Brownian motion, a distance out of this metric tensor, but because this field is very bad, this is just a formal construction you have in mind, and actually it's very difficult to make rigorous the various elements you want to construct out of this metric tensor. So, but let's say a few words all the same. So you can construct a volume form associated to this formal metric tensor. Okay, this is the Liouville measure, and I gave a few minutes ago this expression to you. Okay, so you can also construct a Brownian motion out of this metric tensor. Well, by adapting some arguments, we've constructed some kind of similar things with collaborators, so Christophe Garbin and Vincent Vargas, and Nathalie Berestiki also studied this object. You can adapt a bit the construction we carried out to this framework and construct a Brownian motion out of this metric tensor. But there is an open question concerning the distance. This is a very nice mathematical question, and there are a lot of ongoing works by Scott, by Jason Miller, and by Bertrand Duplantier. Okay, so basically, maybe you can have a word. If you have a Riemann surface, okay, you can. If this is a Riemann surface, you can Riemann manifold. You can look at the tangent plane at some given point. Here on this tangent plane, you have say an inner product because you've got a Riemann manifold. Okay, so you get an inner product. So I have two orthogonal vectors, and you can draw the balls on this tangent plane of your inner products. Okay, and if you try to go from the classical picture that you've got here, and you all know, to this quantum picture here, you should have the Liouville quantum field theory. Here you should have its tangent plane, and here the growth of balls here are the quantum Loebner evolution that Scott and collaborators have introduced. Okay, so this is some kind of quantum picture of this very well-known picture that you may have on a Riemann surface. Okay. Well, and there is also a very important question when you have a conformal field theory. This is the exact computation of the correlation function. This is an object which is very similar to the Ising model Clément discussed yesterday. And in the case of Liouville theory, this is called the Doll's formula. I won't discuss this Doll's formula, but I will explain to you how to construct the correlation functions. Okay, so now I'm going more or less to the definition, but before I give the definition, it's nice to have an intuition of what should happen with a word on the classical Liouville theory. So recall that this is the the uniformizing theorem on the sphere. Well, so you are now on the sphere. Recall that G hat is the round metric, and well, you want to solve this equation, okay? And let us assume for a moment that you can do so. So if you can do so, recall that I told you that if you define this metric, you will get a metric with a constant Ricci curvature on the sphere, okay? And the Ricci scalar curvature will be negative, and you know that this is impossible on the sphere, okay? There is only one way of uniformizing a surface, and the sphere has positive constant scalar curvature, okay? So, well, the classical way to overcome this problem in classical field Liouville theory is to add some. So you have a defect of positive curvature. You don't have enough on your sphere. You don't have enough positive curvature to find a solution to this equation. So you will choose some places, some insertion points. Say you will fix well, a few points, the zi on the sphere. And at this point, you will plug a lot of curvature, okay? And if you want to put a mathematical framework to this claim, you just add some direct masses in the right-hand side of your Liouville equation, okay? If you do so, you can hope to find a solution to this equation. And actually, you find a solution as soon as the Gauss-Bonnet theorem is satisfied. And basically, the Gauss-Bonnet theorem tells you that just integrate this relation here, and you just get the relation sum of the alpha I minus 4 must be positive, okay? And you've got another relation that all the alpha I, all the singularity, each time you plug an insertion curvature bump here, you destroy a bit the shape of your surface, and this blowing up must not be too strong. And this condition reads like this, okay? So if you satisfy these two conditions, this is the Gauss-Bonnet theorem, you can find a solution to this equation. And actually, this tells you that you must have at least 3 insertion points, okay, to find a solution to this equation, okay? So if let's keep this picture in mind, and if you just look at the shape that your new metric has when you do so, you will have some peaks, okay, on your surface. Okay, you have some power singularity at some places. Okay, now let's come to the quantum field theory. So, in the beginning, I want to give you the formal thing you want to construct. Okay, so here, this is just the exponential. This is literally the exponential of the Liouville action. Okay, you have the gradient, the squared gradient here, the curvature and interaction, and the formal dphi measure. But you know that the classical field theory doesn't work like this. You have to plug some kind of quantum bumps of curvature, and these quantum bumps of curvature will correspond to the exponential moments of some field, which is called the Liouville phi. Okay, so you define the Liouville phi as this quantity here, and you plug inside this exponential moments. Okay, this will play the role of your curvature bumps, but in the quantum. Okay, so if you do so, you have at least some formal expression, and now you try to give sense to this expression. Here you recognize the GFF measure, more or less. Okay, so you want to replace this quantity here by the expectation over the Gaussian free field. Then you will have some nice functionals of the Gaussian free field. This is just linear, and then you'll have a chaos measure here. Okay, and well, here you will have this exponential weight of the Gaussian free field evaluated at some point. Okay, so this expression here at this point is not quite rigorous because you cannot evaluate the GFF at some point. But this is easy to give some rigorous definition to this term here by playing with the Kirchhoff transform. Okay, this is just the exponential of Gaussian, so you will shift. Okay, so this is very this is not really a problem. Okay. So and here you have so the exponential with respect to the Gaussian free field correspond to this term here, but there is some additional subtlety here. Actually, the thing that you've got here is not really a norm. It is a zero over constant function. So there is some kind of neutral direction for your Gaussian free field. And if you want to take this neutral direction into account, this will give you an extra integration over the Lebesgue measure, and actually you really need this extra integration to get conformal invariance in GN. Okay, so this is the partition function to which you give rigorous sense. Okay, so if you have an expression for the partition function, the question is now, is it non-trivial? The answer is yes, provided that you satisfy some bounds. So here, this is the Seiberg bound. This is in order for the singularity to be integrable with respect to the chaos measure that you've got here. Okay, so this is just the Seiberg bound, and this condition here can be seen as some kind of quantum Gauss-Bonnet theorem. Okay, this is the Gauss-Bonnet theorem, and this is the quantum version. Okay, so this is kind of analog that you've got in the quantum theory. So, and you see that if you want to satisfy this condition, you must plug at least 3 insertions in your partition function. Okay, so if you can construct this partition function, you can play with this partition function and show that it satisfies the main properties you expect from a conformal field theory. So there are a lot of scaling relation, as Clément told you yesterday. So if you just want to see the dependence on the cosmological constant, so recall that in your Liouville functional, you've got 1 over 4 pi. You have the gradient square plus okay, so the thing is now, this is the Liouville functional, and you want to study the dependence of your partition function on the cosmological constant. So you have a nice scaling relation, which is called the KPZ scaling law. You may also want to know how the way your partition function behaves when you apply a Möbius transformation to your points. So this is pretty much like in the Ising model. So you have correlation functions. You evaluate your partition functions at different points up to a Möbius transform, and you want to see how this partition function behaves. And you have got an expression which is very similar to Ising model, except that here you have some conformal weights. As far as I remember yesterday, it was 1 over 8. Here you have the conformal weights which have this explicit expression. And this formula here is called the KPZ formula by KPZ like Kiznik, Polyakov, and Zamolodchikov. This is the way they originally derived this KPZ relations. Okay? And yesterday, Clément told you about something that you've got in conformal field theory. This is the central charge. He presented it in terms of Virasoro algebra and stress energy tensor. This is not the path I will follow, but this is somewhat equivalent. Okay. In fact, you can define your partition function on the sphere. I mean, the construction I gave you was about the round metric on the sphere, but you can take any conformally equivalent metric to that of the sphere, and so you got the metric of the sphere up to a conformal factor here, and you can define this partition function for this conformally equivalent metric. Okay, and you want to see how this change of conformal metric is seen by the partition function. Okay, you want to quantify this quantity here. So you've got an explicit expression, and actually this is typical for this. So this term here is the Liouville equation, the Liouville functional, up to the fact that you've got a mu which is equal to 0. So this is the Liouville action. Okay. So for any conformal field theory, you should have something like this. The way the partition function reacts to change of conformal metrics is a constant, which is called the central charge, times this Liouville functional. Okay, and here this constant is called the central charge, and here in Liouville theory it is given by 1 plus 6 times q squared. So q varies from 2 to infinity, and so you can have any values between so 25 and plus infinity, depending on the value of gamma you choose. Okay. So it's over. Yeah. Okay. I can stop here. Thank you very much for your attention.
Questions?
you you've got a conjecture for the scaling limit of uniformized triangulation with 3 mark points as your stuff with the 3 conical singularities that you plugged in. Do you have a conjecture, a belief for what would be or how to interpret your object with 4 or 5 or as the scaling limit of a discrete model?
Yes, more or less. We have conjecture when you you need 3 points to send to fix the Möbius transform, and then you can choose another point, but the location will be given by your Möbius transform. Okay, so there is a constraint on the location of the fourth point. Okay, and if you do so, you can interpret this correlation function as the density of points that you have in your triangulation around this fourth.
But if the fourth point is not prescribed by the location,
then you have to apply some conformal field theory machinery to guess what should be the dependence on. But well, if the location of the fourth point is well chosen, I mean, okay, you can have an interpretation for as many points as you want, at least 4. But then if the constraint, you have some algebraic constraints otherwise.
Do you know what happens in higher genus if you do this in...
Sorry?
What happens in higher genus?
Yes, this is a very interesting question. Well, let's say that, it's more complicated. This is why we studied the sphere. But we are not, because you can do this for all Riemann surfaces, and each Riemann surfaces has its canonical fractal geometry which correspond to this thing, and of course it's interesting to look at all the surfaces. And now we are studying the stores actually, but the tori, sorry. But for the tori you have a lot of different complex structures on your tori, and the properties of the Liouville quantum field theory that you will get will depend on the moduli. There will be some modular invariance in the game, but it will depend on the moduli. And actually, it's hard to figure out how the moduli will play on your partition function, because you have to represent your moduli in terms of another conformal field theory, which is called the Gauss CFT. And you have to analyze this partition function of moduli, and this is a tricky stuff, but we are trying to handle this. Okay, so well, the situation depends on the complex structure, but you have some extra CFT to deal with.
Could you just comment on the last line that you didn't talk about, and in particular, do you conjecture that your partition function is somehow related to a regularized determinant?
Well, in some sense, it's not related. It's related because in our derivation of this theorem here, we use some results about the GFF. Okay, but now the question is if you want to apply determinantal regularization to the directly to this Liouville action. I mean, say just for the Laplace-Beltrami of the Liouville quantum gravity or something. I'm not sure at all of the answer. I cannot. Well, this is a very tricky computation. We tried to make it, but we don't manage to do so. Okay, but in our theorem we use this computation for the GFF partition function. But we cannot relate this result to some determinantal regularization of something.
More questions. So, so let's say I want to look at discrete triangulations with 3 marked points. Maybe I have a percolation model or an FK cluster model, and I want one of the points to be on the boundary of a macroscopic cluster. I want one of the points to be at the intersection of 2 macroscopic clusters, and one to just be any old point. I mean, is this like the sort of thing that you can...
Okay, so you want, just to be sure that I understand the question. So you have your percolation and your triangulation, and you want to you want to condition to have the insertion point on the cluster of something.
And sort of I want them to correspond to different types of thick points.
Yeah. This will. Yeah, you're right. This corresponds to different time. No, but
It's the sort of thing that I'm trying to figure out what all you count
Yeah.
with these various
I
approximate with these various
I think
partition functions.
yes. I think I understand the question.
Types of insertions.
The thing is that you can have some nice conjecture for all the, they are called the natural observable of, all these operators which have the right conformal weight, I mean, which are conformal invariant, we can try to formulate a conjecture of this type. But if you have some special requirement like that you mentioned, this is this is clearly now beyond our technology, but maybe with some extra effort, I don't know, but I haven't checked this point. I haven't think of conditioning my insertion points to.
Right, so in your thinking, the insertion points are always just sort of quantum typical points.
Yeah, this is
That's
quantum, and we can then when we fix these 3 points, we can play with the density of points at some mark point of the triangulation. But it's not clear for me how to relate this to this percolation thing, or it's not clear. We can interpret this insertion as density of points in your triangulation in the neighborhood of the root or something, but then if you plug something else on it, we have to make some extra efforts.
I just continue this question. Yeah, but if I just play with, say, random triangulation with an easing model on top, may I just insert a primary field like an energy density? I mean, when I consider not a special, like a thick point in the percolation, but just, reweight
Yeah,
whatever speeds.
yeah. The thing is that if you plug an Ising model on your triangulation and you want to study the scaling limit, there are 2 different things in the limit. There is the geometry of the space, and there is the limiting conformal field theory, say the Ising model on your manifold. My conjecture only gives you the shape of the metric, but if you want to study the conformal, say the Ising model on your triangulation, you have to tell me a way of taking a scaling limit of the Ising model on triangulations. Okay, because in the limit it should be independent of the metric.
No, but what I'm asking about is that now typical faces or whatever points are chosen not uniformly with respect to the triangulation itself, but with respect to some other partition function on that.
Yeah, no.
Does it just lead to a change of the cone weights?
Yes. Actually, for instance, it's more easily understood in the case of the Gaussian free field. If you couple a Gaussian free field to the triangulation, okay, you should in the end you should have some observable which are like this. Alpha, say one Gaussian free field, the one of the metric, and plus another one, beta y, say the Gaussian free field on your triangulations, okay, and so you have 2 independent free fields in the limit, and you require this operator to be conformally invariant. So this gives you a relation between alpha and beta, which are the observable of your, and this relation is exactly the KPZ relation. So for the free field, if you have this observable here, this will correspond to the primary field of say your free field theory. And depending on the primary field you want to study here, you will get some gamma sig or alpha sig point something. They will depend on alpha, but you will be on different alpha sig points.
Yeah, okay. That's the usual expectation that you should get for the alpha the ones which obey KPZ.
Yeah.
Depending on the operators,
yeah,
you want to select in your Ising model.
Yeah. This is KPZ, which will give you the sig points.
Ok, let us thank Remi again.